probably the same day or the next day. All right. So I think you got about halfway through your last lecture. There was a lecture today, right? I think yesterday. And you got about halfway through it, I assume, through dimension stuff? Cool, sounds good. So I'm still gonna touch on it because why not? But yeah, so let's start with something a little bit abstract. Say that you have a set of symbols, and I'm calling these symbols just to mean that they can be anything, like they could be variables, they could be vectors, they could be whatever you want, right? Say we have a set of symbols, x1 through xn. And remember, we put sets in these curly brackets. I'm going to introduce a terminology called linear combination. So a linear combination of these symbols, again, symbols could be anything. Linear combination is some like alpha 1 times x1 plus alpha 2 times x2 all the way up to alpha n xn, where those alphas, I guess alpha I, is taken from like some field. Yeah, so a linear combination, sometimes I'll use the words like anywhere you can reach from this set of vectors. So using like some combination of these vectors, anywhere, any vector, or I shouldn't say vector, any symbol that you could reach. So any set of symbols you could reach. Does that sort of make sense? Is like a linear combination of stuff. Cool. So that sort of brings us to the next concept I want to talk about, which is span. What does it mean for me to say that I have like vectors v1, let's just say v1, v2, and v3. What would the span of those vectors be, like in words? What does that mean?
Span of those two vectors. So like every space these two vectors.
Yeah. It's, mathematically, it's the set of all linear combinations of those, right? Such that alpha I is in your field. And we just use that F for a field, right? I think I said this last week, but a field is a set of things. I'm going to butcher this because it's not true. What I'm going to say is not true, but it's sort of a set where you can multiply, divide, add, and subtract. So if you can, do all four operations in it, then it's kind of a field. It's not exactly true, but for this course, it's fine. Yeah. So span is the set of all things that can sort of be reached by a set of vectors. What's linear independence? Does anyone remember that?
Vector, not expressed.
Sure. So in other words, say that I had like V3. If it was linearly dependent, right, not independent, dependent, I could write it as alpha 1 v1 plus alpha 2 v2 for some alphas, right? But another sort of way to think about this is by sort of bringing v3 to the other side, we get alpha 1 v1 plus alpha 2 v2 minus v3 equals 0. The zero vector here, right? And in front of this v3, I have a -1, right? I'm just going to make it a little bit more abstract, and I'm just going to call it alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3. So if you want to take alpha 3 to be -1, that's fine. Good with that? So with this, if we were to find some set of values from our field, alpha 1, alpha 2, and alpha 3, such that this holds, where those alphas are not 0, because obviously if the alphas are 0, this is going to hold, right? It has to. But if you can find other numbers that go in there, such that it's equal to 0, but all of these alphas are not 0, then we say it's linearly dependent, right? maybe one of them is -1, and then the other two are whatever you would have had for alpha 2, or alpha 1 and alpha 2. Does that make sense? Cool. So with that, so yeah, this gives us sort of a, I'm going to say it's a better definition. And the reason I say it's better is because it's more mathematical and it's more symbolic, right? So like when we say in words that like, you know, sort of hand wavy, like one vector can be represented by a linear combination of other vectors, like what does that even really mean, right? But if we have this statement here, 0 equals alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3, and we say that, how do I say this? If the only solution to this is well, we'll just try again. Anyways, so yeah, if you take a basis is a set of vectors. So maybe that's a good spot to start. It's a set of vectors such that if you take the span of that set, it's equal to the whole vector space. So you can reach any possible vector in the vector space. But they also have to be linearly independent. So that means you can't represent any one of those vectors as any linear combination of any of the others. That's a basis. Now, basis, there's like any vector space can be represented using a bunch of different bases, right? Like you can use, for example, if we were considering like R3, let's say, you could use a basis of, let's see, 1, 0, 0, 0, 1, 0, and 0, 0, 1 as a basis, right? I think that one makes decent amount of sense. You can represent anything and it reaches, right? They're not linearly independent, or they're not linearly dependent, sorry. Another set you could look at, maybe it's harder to see, is something like this. So 1, 1, 0, 1, 0, 1, 0, 1, 1. Like that. So there's a bunch of different bases you could pick. In fact, I think there's, for most cases, there's infinitely many bases, right? So it doesn't really matter which one you pick, but there's something that's interesting about them, which is that regardless of which set of basis vectors you pick, whichever basis you come up with, it's always going to have the same number of vectors. So in this case, in R3, it's always going to have 3, right? And I think this comes, like it doesn't feel as amazing as it is that this is true to most students, but it's actually pretty incredible. Let me sort of talk through it. So with span, as we add vectors to that set, right? So say we start off with just a singleton, just one vector in that set. Its span is obviously, well, maybe in some cases it'll reach the whole vector space, but for most vector spaces it's not, right? The span of one vector is not going to reach the whole vector space. So then you add a vector, and you keep adding vectors, and that spanning set gets bigger and bigger and bigger, right? Until eventually it reaches the whole vector space. Does that make sense? So like, you sort of plot that over, I don't know, adding vectors, it's sort of going off, and then it's plateauing once it reaches, the span is equal to the whole vector space. Because once the span is equal to the whole vector space, you can't get the spanning set any bigger, right? By adding more vectors, because they're always going to be in that space, right? Does that make sense? But then there's another interesting thing, which is with linear independence. If you just take one vector, it's obviously linearly independent, right? Because there's only one vector. If you add a second vector, maybe it is, maybe it isn't. But if you keep going, there's a certain sort of threshold. After that threshold, it's always has to be linearly dependent. So there's sort of a special number of vectors where like those two ideas meet. And that special number is the dimension. That's why the dimension is so cool. And that's why this is like not trivial at all. Does that make sense? Any questions about that? Cool. The last thing I sort of want to talk about is that it's possible to have an infinite dimensional vector space. So most vector spaces that we deal with are finite dimensional, especially in this course. I don't think we'll go too far into infinite dimensions. But consider, are we familiar with this notation? If I do like R to the R.
It's not a real number. R of the set.
You're getting there. Yeah, you're sort of there. So it's like, yeah, you're sort of getting there. Maybe the notation is a little weird. If you think about it, it probably will make sense. This is, got it? Instead of, I'm gonna say no. It is weird. It's a weird notation, but this just means the set of all functions from R to R. Yeah, it's the set of all functions from, and the way you would read this is if I did like, say I did like A to the B and these were both sets, it would be the set of all functions from B to A. So it's kind of backwards. It's a weird notation, but that's what that means. If you ever see like a set to the power of a set, that just means the functions from the top to the bottom. So if we consider this set R to the R, that's the set of all functions. It forms a vector space. Maybe you don't believe me, but it does. So clearly that has infinite dimensions, right? Because there's like infinitely many functions, right? Like it's so undescribably large, that set. You could even just start by saying, well, what if we consider the set 1x squared all the way up to like, well, infinity, right? And keep going. So you've infinitely many basis vectors, and that's only dealing with the polynomials, right? We start talking about like cosine and sine and exponential and rational functions, like this is going to get huge, right? It has infinitely many functions in its basis. So it's an infinite dimensional space. Does that make sense? Cool. Okay, with that said, I'm going to stop this recording and try and merge them together later.